Hello everybody. In this video we'll be covering one of the sections in chapter 4 of our textbook entitled Atoms and Elements. In this video we will be discussing isotopes. So the presence of isotope has to do with the structure of the nucleus. And it all started with this guy by the name of Sadi. And what he discovered was that the same element could have atoms with different masses, which he then called isotopes. An example of this would be like chlorine, where we know that some of it, the majority of it found in nature, has a mass of 35 AMU, while there's another one that's present in about 1/3 of each of the chlorine atoms is going to be have a mass of 37 AMU. The observed mass is a weighted average of the weights of all naturally occurring atoms. Okay, so this is where we're getting the atomic masses that we're putting on the periodic table. What we do is a weighted average, and we'll talk about what mathematically that is a little later. Basically, we're going to do an average that's going to take into account how much of the chlorine is present at 35 AMU and how much of it is present at 37 AMU. And we're going to report that average on the periodic table. So that's where these fractional AMU are coming from. So all the isotopes of an element are chemically identical. Okay, so they undergo the exact same chemical reaction. So we don't have to worry about that when we start talking about isotopes. They're still going to behave the same way that they always did. And we're still going to have the same number of protons as we've been discussing. An element is defined by the number of protons that it has, and that's still going to hold true. But the isotopes of the element are going to have different masses. And the reason that they have different masses is that they actually have different numbers of neutrons. It just happens to be true that given a certain number of protons, there are different nuclear configurations that are stable that have different numbers of neutrons in them. To help us talk about this and identify the isotopes, we're going to define a new number called the mass number. And the mass number is going to be a whole value that is the number of protons plus the number of neutrons. So let's talk a little bit about some of the things that the language that we have so far. So we have our atomic number. This is going to be the number of protons, and it's going to be abbreviated with a capital Z. And now we have our mass number, which is the protons plus the neutrons. This is going to be a whole number, and it's going to be abbreviated with a capital A. And we also have something we're going to call the percent natural abundance, and this is the relative amount found in a sample. So if you took any specific sample of, say, neon or something like that, you're going to have an isotopic distribution in it. Okay? So if we look a little bit more carefully at that, in the case of neon, about 90.48% of it is going to exist as neon 20. It's going to have 10 protons and 10 neutrons, which gives it an overall mass number of 20. That's 10 plus 10. A very small percentage of it, 0.27%, is going to exist as neon 21. In this case, it has an extra neutron. Okay, so it's now got 10 protons, 11 neutrons, which sum to a mass number of 21. And to make up the balance, about 9.25% of all neon is going to be existing as neon 22, where we have 10 protons and 12 neutrons for a total of mass number of 22. So chlorine 35 makes up about 75% of the chlorine atoms in nature, and chlorine 37 makes up the remaining 25%. So I said it wrong. It wasn't a third. It's a quarter of all chlorine is chlorine 37. The average atomic mass of chlorine is 35.45 AMU. Chlorine 35 has a mass number of 35. That's 17 protons and 18 neutrons. And the way that we're going to express that is when we want to be specific about the fact that we're talking about chlorine 35, is we're going to use this notation right here. Okay, so we're going to use its elemental symbol. We're going to write its atomic number here, and we're going to write its mass number as a superscript next to it. So now we're being specific about which isotope of chlorine that we're talking about. So let's go through here and talk about how many protons and neutrons there are in an atom of chromium 52. Okay, so this symbol alone allows us to determine both the number of protons and the number of neutrons. So what are we given? We're just given a symbol here. Okay, we know first off that the mass number is going to be 52 and the atomic number is going to be 24. So we know that the mass number is the number of protons plus the number of neutrons. And we know that the atomic number is going to be the number of protons. So that means that Z here is equal to the number of protons. And if we take the mass number minus the atomic number, okay, so they're going to sum together to give us that. So we would subtract off A minus Z, then we will get the number of neutrons at 28. And then a little check that is pretty useful is that for most stable isotopes, you should be getting a number of neutrons that's greater than the number of protons. And that holds true until you get to be really, really large atoms down at the bottom of the periodic table. So, in summary, if we want to know the number of neutrons, we're going to take the mass number and subtract the atomic number, and we're going to remember that if we want the number of protons, that is the same as this atomic number, which we're going to put in the subscript here. And also, do remember whenever you're seeing these, that you should always have the larger number up top. Okay, if you ever see one that has a smaller number up top and a larger number in the bottom, you've written it wrong, or it is the incorrect answer to a question. So let's do a little practice here. I'll give you guys a moment. For calcium 40, carbon 13, and aluminum 27 as a ion, a +3 ion, I would like for you guys to write down the atomic number, the mass number, the number of protons, the number of electrons, and the number of neutrons. Okay, so if we come in here, our atomic numbers we would have looked up from the periodic table for calcium, carbon, and aluminum. We'll recognize that these atomic numbers are going to be the same as the number of protons. For calcium and carbon, we have neutral, non-ionized species here. And so in those cases, the number of electrons are going to be the same as the number of protons. But for aluminum 3+, we have this +3 charge, which means that it lost 3 electrons. So we're down 3 electrons for this compared to the 13 protons for aluminum. The mass numbers are given to us in this format here. Remember that this is another way that we can write this. You can write out the name of the element with a hyphen and then put its mass number to be specific about an isotope, or you can put the symbol of an element and a hyphen and then note its mass number. So we're given those directly. And now from the mass numbers, we can figure out the number of neutrons. It's going to be the mass number, which is the number of protons plus neutrons, minus the atomic number to give us the number of neutrons. So I want to make it very clear a distinction that we're making now in this chapter based on the way that we've been talking about this so far. So far, we've been talking about the mass of an atom, and we were basically interchanging between mass number and atomic mass. Uh, and really, they're two different things. So the mass number, as we've been talking about, is the number of protons plus the number of neutrons, and it's specific to one isotope. The atomic mass, though, is actually an experimental number, and what really is happening here is we have been making the assumption so far that a proton is about 1 AMU and a neutron is about 1 AMU. But that's actually not strictly true. The neutron is actually a little bit heavier than a proton, and due to some very interesting chemistry that we really don't fully understand yet, uh, the mass of a nucleus can be different given these different configurations that they have. And really, this is an example of our theory not really keeping up with our ability to measure things. So we don't yet have a model that would allow us to calculate the exact mass that we can measure now for each one of these different atoms. So we're able to measure them very, very precisely, and we can see that there's some slight variations in the mass that you would predict for the various atoms. And to make this even more complicated, there's an atomic mass for each individual isotope, and there's an atomic mass that we actually report on the periodic table that takes into account all the naturally occurring isotopes. And what we do is we do like a weighted average of the atomic masses of the individual isotopes, and we take into account their natural abundance. So let's see how that math works out. So in this example, we have gallium-69, and we have its exact mass right here, 68.9256. And you can see what I was talking about before, that we don't get exactly 69 when we go and make the measurement. Because we're able to make the measurement so precisely, we can see that it's a little short of 69. And it's out of all the gallium, 60.11% of it is in the form of gallium-69. And we have gallium-71. And again, we have its mass, which again is a little bit less than an actual 71. And it has an abundance of 39.89%. And we're going to be asked to calculate the atomic mass of gallium, meaning the atomic mass that we would report on the periodic table. The first thing I do want to note here is that we have 60.11% and we have 39.89%. If we sum these together, we get to 100%. So that means that all gallium is in the form of either gallium-69 or gallium-71. And we need to take into account all of its forms in order to correctly calculate the atomic mass. And we can do that in this case. So let's talk about what we're given. We start off with the fact that we have gallium-69, gallium-71, we have their natural abundances, and we have their masses. We're being asked to find the atomic mass in AMU. For our solution map here, we're going to take the isotopic masses, the masses of each isotope, and the isotope fractions, and we're going to find the average atomic mass. And what I mean by isotope fractions is these values converted over to decimals. And we're going to use this equation that can look a little confusing to you guys if you're not used to this type of notation. And basically all this sigma here, that's a capital sigma, means is that we're going to add up all of these values. So what we're going to add is we're going to pair the fraction abundance of the isotope, so these values as a decimal, okay, multiply by their masses, and we're going to add across however many there are. All right, so this notation allows us to talk about what we're going to do independent of how many there are. So in this case we have 2, but you could have more, right? You could have one where they have 5 different isotopes, right? And you would just add each one of the isotopes up. So mathematically what we do is we convert this value to a decimal, we multiply it by its mass, and we add to it, this guy is a decimal, and this guy's mass right here. And then we just do these multiplications and add them together. And when we're done, we get 63.723041. All right. And then we need to figure out where our significant figures lie. In this case, with the information that we had this to 4 significant figures. So we're limited to 4 significant figures. And we would report on our periodic table that the mass of gallium is 69.72 AMU. And as a little check, we're going to see that this value here is just a little bit closer to 69 than it is to 71. And that's because most of the gallium is in the form of gallium-69. And that's what this weighting does. It takes into account the fact that there's a little bit more, that there's more gallium-69 than there is gallium-71. Another good check is that the average needs to be between the 2 masses, okay? You can never come up with a value that's going to be smaller than the smallest value or larger than the largest value of mass. So now I'd like for you guys to try one for yourself, okay? In this example, we have copper. And we know that 69.17% of it is going to exist as copper 63, that it has this exact mass here, and that the rest is going to be in the form of copper 65, and it's going to have this exact mass here, okay? I'll give you guys a little hint. The first thing we need to do is figure out what the rest is, meaning we need to take 100% and subtract out this 69.17%. That'll tell us how much of the copper exists as copper 65. So you can pause the video and take a moment to work on that. All right, if we go through this problem here, we'll start off with our givens. Our only difference between our last problem is that we did have to calculate this percentage here. Again, that's going to be 100 minus 69.17, or 30.83% if you did that math out there. We're being asked to find the atomic mass, and we were given the same sort of information to start off with. So our solution map is going to be the same, and we're going to be using the same equation here. When we go through our solution, we're going to, again, remember to convert these percentages over to decimals and then multiply them by their corresponding masses. Make sure that you pair these correctly, okay? And don't get yourself confused. The 0.6917 goes with the 62.9396, and similarly, this set of data is in a pair here. We add those together, and we adjust that to 4 significant figures, and we get 63.55 AMU. Again, we wound up with a value that's between our 2 masses and closer to the major isotope. In this case, 62.9. We get 63.5, which is a little closer to that value than it is to the 65.